Hi, in this video I'm going to follow the discussion in this reference, A First Step Towards Variational Methods in Engineering by Francisco Periago. There's a discussion on mathematical background of finite element method. In particular, I'm going to introduce the idea of distributions. So I'm going to introduce this same material. You can refer also to this chapter for an alternative picture of the same ideas. All right, so let's go there. So let's start with this equation, which we derive from the consideration of heat flow in a rod. Remember that U is a function of x, kappa and lambda and f are functions, and here this is for x between 0 and L. Now we mentioned that this equation can also describe the displacement of a string. In this interpretation, F is a force. Now force is associated with work or energy. If you take a force and you apply over a distance, that produces a work or energy. So we can create a displacement function v, which is a function of x, and we can multiply that by f. And since v varies over the length, we want to take a sum of f times v over the length, which in the continuous approximation becomes an integral. So when we multiply this by a displacement function and integrate, we get the following result. I've just integrated every single term from 0 to L. So let's focus on the right-hand side. What does the right-hand side do? Now my displacement can be arbitrary. So for any displacement function, this right-hand side gives me a real number. So in other words, we have a mapping. We can associate functions with real numbers through this mapping. Right? Every function, I take this function as my input. I integrate from 0 to L of f times that function, where f is a fixed force. So this associates with a function a number, and that's called a mapping. This kind of mapping is called a functional. You can think of it as a function defined on functions. Remember, a function defined on real numbers assigns a real number to a real number. Here we're assigning a real number to functions, so we can consider this a function on functions or a functional. All right, now let's be more precise about the domain of this mapping. We're taking functions to numbers. Let's define a specific domain for the functions that we're looking at. And here's a domain that turns out to be convenient. It's called script D, and script D is defined on function. Script D is a set of functions on the interval from 0 to L. And here I have open interval from 0 to L, so 0 and L are not included. And these are all C infinity functions on 0L. C infinity means they have all derivatives. Okay. One additional property is it has compact support. Compact support means that the function is 0 outside of a closed interval. So let me draw a picture here of a function with compact support in 0 to L. All right, so let's see. Going from 0 to L. Here's our axis, so from 0 to L here. Now, remember that 0 and L are not included. So a function with compact support is 0 outside of a closed interval. And it has all derivatives, so it has to be smooth everywhere. So this function could look something like this. It has to be 0 out here. Sorry, it's not working very well. Not sure why. Here, let's make it a wider function here. I'll make it like this. Okay. Make it wider. Okay, so 0 here. And then here it can start to go up. And it has to go down again. It has to go smoothly down to 0. because it has to have all derivatives 0, and then it's identically 0 here. So the function is identically 0 here, identically 0 here, and there's a smooth transition from 0 to non-zero values. Okay. So the set of functions script d from 0 to L is called the space of test functions on the interval from 0 to L. Okay. In particular, since the function has compact support, it means it has support inside a closed interval, which means that it cannot be non-zero at the two endpoints. So the function is 0 at both endpoints. That turns out to be important later. All right, now, one other fact about the mapping is the mapping is a linear mapping. So what does linear mapping mean? Okay, linear mapping means that if I take a combination of two functions, for instance, I could take c1v1 plus c2v2, okay. According to this mapping, that will go to okay. And I can write that as c1 times the integral from 0 to L of fv1, because the integral is linear, plus c2 times the integral from 0 to L of fv2. Okay. And these are the separate mappings of v1 and v2. So the mapping of a linear combination is a linear combination of the mappings. All right, so this is a linear mapping. Now, in the case where the function f is differentiable, then we can use integration by parts to evaluate the integral from 0 to L of f prime of v dx. Okay, so in fact, we'll find out that this is another mapping from the set of test functions to the real numbers. So let's evaluate this. F prime v, using the product rule, we say f prime v equals fv prime minus f times v prime. Okay. When we integrate the first term by the fundamental theorem of calculus, we get the difference of function values at the two endpoints, and then we subtract this remaining integral. Now, since v is a test function, the value of v at 0 and L is 0. So this term goes out, okay, since v is 0 at both endpoints. So we get this relation that the integral from 0 to L of f prime v is equal to negative the integral from 0 to L of fv prime. Right. Okay. So this is also a linear mapping, which you can verify. If you take c1v1 plus c2v2 and apply this mapping to it, you will get the corresponding linear combination of the mappings of v1 and v2. Right? Okay. Now we call this linear mapping, we call the original linear mapping the distribution associated with f. Okay. This is the original linear mapping. V goes to the real number, that's the integral. Now, we can also have this second linear mapping where you take the integral from 0 to L of fv prime with a negative sign. This is called the distributional derivative of f. Okay, so here's the distribution associated with f is a linear mapping. This second linear mapping, which is derived from the first, is called the distributional derivative. An example. Suppose we have a function that is defined in pieces in this way. Now you can see that this is actually a step function, right? I encourage you to graph this function. Okay. All right, so exercise, evaluate the distributional derivative of this function. Remember, distributional derivative is just given by this expression. So what you need to do is put this function in to You need to put this function into this expression and evaluate it for arbitrary v. And it turns out that this distributional derivative may be identified with an impulse. All right, you'll find out that the expression, when you evaluate the integral of f v prime, you get a very simple result. Okay. Now remember, v is a c infinity function that is 0 at 0 and also at 1. Because in this case I'm looking at 0, 1, so my L is 1. All right. Now, the distributional derivative of a function may often be associated with another function. So here's another example. F of x equals 1 minus the absolute value of L over 2 minus x times 2 over L. You may notice that this function takes the value 1 at L over 2 and 0 at when x equals 0 and x equals 1. X equals L, sorry. So I encourage you to graph this function and see what it looks like. Exercise. Find a function g of x such that the integral from 0 to L g of x v of x is equal to the integral from 0 to L of f of x times v prime of x dx. In other words, take this function, integrate it, compare to the derivative of v, use integration by parts, and you will find that you can re-express this result as an integral of a function times v. Okay. Right. You'll have to break the integral into two parts because this function has two smooth pieces. Right? The piece from 0 to L over 2 and the piece from L over 2 to 1 to L. Right? Okay. So in summary, what have we done? We've defined the distribution associated with a function. So the distribution is a linear mapping that associates functions with numbers. We've used that distribution to define the distributional derivative of a function. Now, the distributional derivative of a function is often associated with another function. So this gives us an extended definition of derivative that is more general than the usual derivative. So the important point here is the distributional derivative is a generalization of the regular derivative. Okay. So we can interpret differential equations in a distributional sense. Okay. In a distributional sense. And we can get more general solutions to differential equations and partial differential equations. Okay. So that's the idea I want to leave you with. We have a more general notion of differentiation, which enables us to get more general solutions to differential equations. Okay, that's it. Thanks for watching.